Hello, everyone, and welcome to the summit. Thanks for attending this session. I'm Neel Phadnis. I work in developer ecosystem, and I'll be presenting, but would like to thank my colleagues, Kevin Porter, Meher Tenjukian, and Piyush Gupta for their help in putting this session together. Kevin is here. He is managing the Q&A channel. Thanks, Kevin. And I'll be taking your questions at the end of the presentation. Please use the Q&A interface to submit your questions. In case we are unable to get to some of your questions at the end, we will definitely get back to you. But please also join the Slack channel that's available in Developer Hub to continue the discussion. So the session is about developing for strong consistency. So that basically leads to the question, what is strong consistency? And the famous CAP theorem basically states that in a distributed system, if it has to continue to operate in case of partition, it has a trade-off. It has to make a trade-off, and the choice is between availability and consistency. Many NoSQL databases choose availability with the promise of eventual consistency, and that's fine. But when it comes to assured consistency, there are problems. There can be stale reads, lost writes, and it may not ever reach consistency if it has steady stream of updates coming. With Aerospike, there's a choice available. A namespace can be configured for strong consistency or SC mode, which is equivalent to the CP mode in the CAP theorem, or availability, the AP mode. And in the strong consistency mode, all replicas are synchronously updated, and we keep only one version of data, no forks or merges, and the consistency is immediate, and only one version is preserved. So the strong consistency mode guarantees that there's no data lost. If the write is committed, it is durable. There's no dirty data seen in the middle of an uncommitted transaction or committed transaction. You don't see any dirty data in the middle, and no stale data is also seen from last uncommitted write. So all these guarantees have been validated by Jepsen tests in Aerospike 4.0. They have been available since Aerospike 4.0 version. They've been validated a couple of years ago, and Jepsen test is a standard when it comes to consistency in distributed systems. But there's more to strong consistency, and it's more than just keeping the replicas in the cluster synchronized, consistent. There is also the consistency between application's knowledge of the state of the database, what was the outcome for transaction, and the actual outcome in the database. Because there could be, and this gap arises because certain transactions may be in doubt. There can be ambiguity, and we'll see this in greater detail. And this particular session, Developing for Strong Consistency, is mostly focused on how do you take care of resolving these differences between application and the database. So how to develop for strong consistency? So first and foremost, it's very, very important to realize that Aerospike is different. All the databases that you might have used in the past, Aerospike is different, and that's why you have to do certain things differently. Aerospike has been designed for speed at scale, which means, and the design philosophy has been keeping most common operations simple and predictably fast. The corollary of that is to differ if there are operations that are not as common and introduce complexity that might slow down the common operations the onus will fall on application. So with that, a few things to point out. The transaction boundary or the scope of transaction is a single request and single record. So you can have multiple operations on the single record in a given request, but the boundary is single request, request and single record for a transaction. So because the transactions cannot span multiple requests, the control APIs like commit, rollback, etc., are not needed and not there in Aerospike API. The updates are for single bin. So specifically, that you cannot send any custom logic to the server for execution. You have to bring in the data to client for arbitrary updates and then send writes back to the server. There are exceptions in two specific exceptions. I mean, UDFs that people who are aware, user-defined functions, they're kind of stored procedures that they reside on the server, not recommended, not suited for strong consistency. They have great use cases, but strong consistency, they are not the best use. And we don't have to go into detail there. The other point I want to mention is a lot of the operations are enabled on the server side. If you look at some of the complex data types, they take care of efficiently executing some of these updates on the server side, but they are not arbitrary updates. If you have custom logic that needs to update the data, then it has to be typically done on the client side. Last but not least, there's a smart client library. The nature of Aerospike cluster is it is dynamic and adaptive, and it is recovering from various changes, transitions, and failures. Nodes come up and nodes go down, and so on, and during which the data will migrate within the cluster. There is a smart client component with which application links is keeping track of all these changes that are happening in the cluster and keeps the application separate. The application doesn't have to be weighed down by these details. And the smart client library is taking care of it and directly routing the request to the right node. And a takeaway from this particular point is the retries can succeed. So just because you've got a failure or exception, some retriable exceptions must be retried. So let's quickly go through how a write transaction looks or is processed within an Aerospike cluster. So the client library, the application does a write, and the client library figures out where the master node is. That's where it sends the write transaction. Master node applies the update, processes the update locally, and then it sends the updates to the replicas. There are two replicas here, actually three replicas, including the master, but two other replicas are notified of the update, who in turn process the update locally and acknowledge back to the master. And master, when it receives all the acknowledgements from all the replicas, it tells the client the write has succeeded, and then asynchronously, it also lets the replicas know that the write has succeeded, and now they can sew the version for any subsequent reads. So that is how a transaction is processed in Aerospike. The key point here is while the transaction is going on, various failures can happen at various places. A client can go down, client can crash. There could be network issues, and there could be connection failures. There could be failures on the server side. Any of the replica nodes or even the master node can go down. All of this would mean to the client, what it means to the client is that the outcome of the transaction may not be known, whether it succeeded or it failed. Also, there is a state where it is taking the write or the replicas. It's taking longer for them to acknowledge, and master hasn't received all the acknowledgements for all the replicas. In which case, the transaction can time out, and the client will receive a timeout status with in doubt flag. In doubt just means that the outcome of this transaction is in doubt. It's uncertain. And how common are these failures? Can you take a stance that if it happens very rarely, once in a century, are they worth bothering about? And the short answer is they happen pretty frequently, depending on how big and busy your cluster is. But if you look at some of these examples, timeout can happen with system load or node failures. And depending on, again, your installation, it could be happening very frequently or frequently enough. And connection error similarly can happen with system load, node failures, and so on. And there's a category of application failure. You can have bugs in your application, which can crash your application, and so on. So point is, these cannot be ignored if you want strong consistency within your application. There are two keys to strong consistency. One is you have to model your data correctly so that all the data that needs to be updated atomically has to reside in one record. And there are techniques available. There's a blog post that I mentioned at the end of the slides that basically talks about these techniques. Our focus in this session is going to be the second point, which is how to handle failures and resolve uncertainty. And one of the ways you do it is essentially you have to make the right transactions identifiable so that you can go back and find out what happened with that transaction. And when you cannot, after multiple attempts, you just don't give up, and you do. Basically, the point is you need to get an external mechanism to resolve it, and that can be a batch process that looks at some of these in-doubt transactions, or it could be actually a manual intervention. So in order to enable that, you need to make all the details available through logging or other means. So I think there's a quick poll that I would like you to point out. Basically, there's a simple poll that you can take a few seconds. And if you can take that quickly, I would appreciate that. I'll be glad to share the results at the end. And what in this session, we will focus on some common problems in consistency and what are the Aerospike mechanisms and solution patterns to solve those problems. And some of the problems that are listed here are: how do you isolate read and write read-write transactions without locks? There are no locks, and each transaction, each request is separate, atomically executed transaction. How do you combine the read-write into a single transaction? Second problem is, how do you query your transaction status without a handle of a transaction? You have handle for a record, but what happened in the past in that record's history, there's no way to query or examine that. The third is, how do you resolve in-doubt transaction when the server has timed out and it doesn't know exactly what has happened or what will happen in the future? Then there is a problem of idempotent or only once execution. And it's not a problem per se, but if you have it, it makes your recovery from some of these common failures much easier. You can easily retry your write without worrying whether you're doing it multiple times. So we'll look at how do you enable that. And next one is what about multi-record, multi-service? I won't call it transactions because they are not. If they are multiple records, they cannot be transactions. They cannot be atomically updated. But how do you handle those exactly once updates, which happen to be across multiple records? And last but not least, how do you recover from a client crash? So these are the problems that we'll look at. What are the Aerospike mechanisms and solution patterns you can use? So let's look at the key mechanisms that will enable solutions to these problems. The first mechanism is, what are the atomic mechanisms? How do you achieve atomicity? As we said earlier, a single request is atomic on a single record. And in order to, operate is the mechanism to use. What operate allows you to do is take multiple operations in a sequence and send it to the server for execution on a single record. All the operations succeed or none of them succeed. That's the atomicity guarantee. For example, you can update the record, tag it with the transaction ID, and add any chained event that go with the update, all of that atomically. Another atomic operation or atomic mechanism is the generation equality check write policy. A policy, there are multiple policies in Aerospike, and typically they change, enhance the operation semantics on the server. And so the gen equal write policy, what it does is it allows you to specify generation or version of a record that has to be the same on the server if the write has to succeed. If it is different, then it won't succeed. So we'll see actual code and example of it, how it's used. The second useful mechanism, as I mentioned earlier, is how do you make an operation, a transaction, idempotent, safe to retry? Because that makes your code easier. And so a common way of doing that would be you tag something to the operate. You add one of the additional operations to the sequence of operations in operate, and those operations have these qualities that if they are tried again, they would fail with a uniqueness violation, for example. So here, the example is that of you're inserting a unique key in a map with create only map policy. It will succeed the first time but fail subsequent times. And there are other examples of that, such as creating a bin. Another way of doing it is using predicate expression in the operate policy, which gives you a little more flexibility. There are more general conditions that you can use a specified predicate expression. And you could also use similar mechanisms using other data types like list, for example. So these two mechanisms are important. We'll stitch them together when you look at the solution patterns. And another thing to basically look at is what are the data design patterns. As I mentioned earlier, there are data modeling techniques which will help you make sure that an object has all the data that needs to be atomically updated in a single record. And all the object and its relationships, if you are able to keep them in a single record, then atomicity is enabled for that object. And you can use techniques like embedding, linking, denormalization. And there's a blog post that I mentioned at the end of the slides that you can look at. And a couple of patterns that you will see in some of the solutions are, how do you tag a transaction ID It is done by creating a bin or a field in the record of type map where you store the transaction ID and the timestamp as a key value pair. Similarly, if you want to enable an exactly once changed event that is triggered by an update, you would similarly, create a new bin of type map which stores event ID and any event data as part of that map. It could be a list, but the data type is not important. But you can take this pattern and change it for your needs. And the record would look basically, all the data that your application needs and a couple of additional fields to hold the transactions and change event data. So let's look at some of these problems, how these patterns come together, mechanisms, and come together to solve some of the problems that we listed earlier. So the read-write transaction isolation is a kind of common problem that most of Aerospike developers, we have dealt with their Aerospike. This is one of the first things that you probably learned. And the key thing here is enabling the write back of record data with a generation equality check. And the code, it's, I think, best explained with the code, is we are doing a read here in the client get, and when you update it, you specify the write policy of gen equal, and you are specifying the same generation as you read. So meta is a dictionary that holds some metadata, and you're specifying the generation that you read at the time of the read, and the consequence or the result of specifying this is if the generation is still the same, the record hasn't changed by another write, then your operation will succeed. If it has changed, this check will fail, and you'll get this exception generation error, in which case you have to retry the entire read modified write pattern. So let's look at the next next problem in consistency. How do you resolve uncertain outcomes? And so basically, we'll look into the details of it, but there are two, scenarios. One is you look at, specific errors and take care of them. But equally, as I mentioned earlier, if you cannot resolve them because it's timing out the partition, the network, the cluster has split, and it remains in that state, what you need to enable is external resolution of that failure if you want to plug all the holes, if you will, in your application. So log details and let the external resolution take care of it. And this is basically, the first part is just addresses strong consistency, but you need to continue to use the best practices for correctness and efficiency as you would. So let's look at some of the potential solutions for resolving uncertain outcomes. And as I mentioned earlier, there's no API to find out the status of a transaction that happened in the past, such as a write. So some potential solutions which don't necessarily work in a general case could be like, why can't you read back in a loop the write you just did? And so you have to basically read past the generation because you have to make sure that the write has gone through and the record version has been incremented. So you need to look for this. But even if you do that, it could work in some situations when you can recognize the write, and you have the guarantee that others could not have overwritten, the same data. So the problem obviously is there are multiple clients performing writes, in which case another client could have updated the same value, and there's no, or even different value. There, multiple writes have happened since. There's no way of establishing whether your write succeeded or failed. The second, so-called, obvious but not doesn't work solution is just retry. Obviously, it can succeed in some cases when the write is idempotent, or if it fails, certain writes which can happen only once, and subsequent attempts would fail, such as only once operations, as we mentioned earlier, like unique value in a map or a list or a bin creation and so on. They can succeed only once and subsequently fail. And when they fail, you can use the failure to construe that they had succeeded, etc. But those operations, most operations, general update operations are not, they may not fall in these categories. So it's not a general solution. So the general solution is basically tagging a record with a unique transaction ID so that you can identify the transaction with the transaction ID, and you will use the same mechanism to make a retry safe, because as you see in this code, what we are doing is we are tagging the record with the transaction ID. So this is the map transactions bin, which is a map, and you're adding a transaction ID to timestamp key value pair with the map policy of create only, which means that if you try to perform this operation again, it would, if it had already been created, it will fail. And that gives you kind of safe retry mechanism. Here is a housekeeping detail. So you don't want the map to continue to grow infinite if it's a very popular update record. So you want to sort of keep trimming it. And what this is doing is, if the transactions, in the transactions list, if you have timestamps that fall in the range of 0, which is at the beginning of time, to, as much as up to max age old, older than max age, those transactions will be trimmed by this remove operation. This is one way of housekeeping it, but you can do it many different ways, such as after your update transaction succeeds, you can go back and remove the transaction ID from the transaction list. That has more overhead, but it might be more suitable to keep the transaction list in check. And with that, you will see the logic of retry of the write becoming much cleaner. So just a few things to point out. As I mentioned earlier, if you get elements exists error, that can be construed as success because your transaction succeeded in the past that you just didn't know about it for various reasons, as we saw earlier. This is generation that continues. If it somebody else has updated, you continue to retry the read, modify, write pattern. But there are some other failures that are retriable, and you have to retry them carefully. Key thing to remember there is basically you don't want to do them too aggressively, as that would compound potentially the cause that caused the failure in the first place, because system is under load. You don't want to keep retrying too aggressively. So you might want to even introduce exponential back off and so on. That's one thing. Second point is when you are ready to give up because the cluster has split and there is no connectivity to resolve that transaction, you basically log the details for the higher powers to resolve it externally. So at this point, you might ask, if you have to do this for every write in the system, is it too much of an overhead? Because the general mechanism we discussed for the write to be safely retried only once writes, it has cost, it has overhead. You need to allocate map, which takes up space. You need to do, check of uniqueness. You have to insert the key value pair. You need to do trim for housekeeping reasons. So and that seems like a lot of overhead. Can you make it simpler? And the answer is a guarded yes. It depends. It depends on the nature of data. Not all data may need, same treatment. You might have financial data and some usage statistics in the same record. Not all has to be dealt with the same level of care. And so you can make that decision. Occasionally, in the case of failures and ambiguity, you may ignore the transaction status for usage stats, for example. It also depends on the nature of update. Your updates may by themselves be idempotent or even infrequent. That will help you recognize them. So, for example, if the salary is being updated, and that's not a great example because of financial data, but just to make a point here, that is infrequent update, a salary is updated once every month, you can be sure that nobody else could have updated the same value in the recent past. And you can use that data to determine whether your transaction succeeded or not. And if there are any other recognizable data patterns which are application specific, you could leverage them and resolve the transaction status. But that again is, not general purpose solution. Also, the nature of class, your architecture can help you out because if there are a limited number of writers, for example, you can just allocate a separate bin for maintaining a client-specific version in those bins, which can be lighter weight than the transactions map that we talked about. And if there is synchronization across writers at a higher level, then that also will help. So you can use all these different techniques to simplify the solution. So that's possible. So let's switch the gear and quickly talk about a couple of additional topics. I'm not going to go deep into it, but the problem is, what about multi-record updates that can span across services, but they have to have exactly one semantics. And the quick answer there is basically you have to record that event atomically with your update. Then that you have to collect it and post it for the process for processing at the destination at the wherever the second update to the second record has to be executed. You need to post it there at least once, and at the destination you have to process it idempotently because it might appear more than once. So this is the pattern, and essentially this segment or this logic is expansion of this, and you can look at it in greater detail. But for benefit of time, I'm just going to skip over the details. This chart summarizes the problems that we identified or said are some of the common problems in consistency, the solution pattern that we adopted, and what the Aerospike mechanisms or features that are used. And some of the things that we didn't directly touch are also covered in this table that are fairly easy to figure out. One more additional point I want to make is what read mode policy should you choose, because there are 4 SC read mode policies from linearizable, session, allow replica, and allow unavailable. And they all guard you against dirty. They don't return dirty data. They don't allow lost data. But in terms of stale data, they differ. This is a rock solid guarantee against stale data versus there are no guarantees, and other two are somewhere in the middle. We recommend session in most cases. That's the one that you have to go by. Use that, except for in multi-site cluster. There was an earlier session this morning. We talked about what multi-site clusters are, and if you're programming, if you're developing in that environment, you should be using allow replica, which is almost, for all practical purposes, for staleness guarantees, almost as good as the session level consistency, but it has huge performance benefits in the multi-cluster setting. So that brings us to the end. I would like to summarize the points that we covered in this session. The first point which motivates this session is strong consistency requires not only consistency across replicas in the cluster, but also the consistency between application and the database. And it requires application to resolve uncertain transactions and implement safe retries. And we looked at both of those, how to solve those problems. To query and resolve uncertain outcomes, we to tag a transaction with a unique ID, and to achieve exactly one safe retries, various mechanisms can be used, and we saw some examples of that. You can improve upon them. In some cases, your knowledge of data operation architecture can help you simplify and optimize the solution. And if you are solving multi-record exactly one's update problem, then the pattern that to use that's suggested here is to capture the update atomically, collect and post it at least once, and process it at the destination only once. Here are some of the resources that you can download these slides and check out. There are blog posts, documentation, as well as videos, white papers available. And with that, thank you very much for attending this session, and I would be glad to take any questions that you might have. So I'm looking at the questions that have been submitted. So I think I'm going to go through a few of them with a couple of minutes that we have. But I would like to mention that we will definitely get back to you for any unanswered questions during this session. People have the next session to go to, so I don't want to take too much of your time eat into the next session. But we will get back to you by email for any unanswered question. There's also Slack, as I mentioned earlier, that you can go to continue the discussion. And so thanks. From documentation, it's not exactly clear that timestamp and term are included with update counter in generation check. Okay. So Kevin, I'm not 100% sure which the specifics of this question, but Kevin, do you have any insights into this one?
Response to another question. So there's not a clear way to respond to somebody asking a question. Like when I answer it, I think this is a response to my question.
Okay.
Yeah.
Okay. So there's, I'll take a question about the roadmap is pending from a long time as we are using Aerospike since 2014. So I think that you should attend some of the sessions tomorrow and day after. There's a session by Srini and others that will shed more light on the roadmap items, as I think the futures and what is coming down the pike. So I think those I highly recommend attending those discussions. So I think we are unfortunately there are a few more questions, as some of them have been answered, but I see some unanswered questions that we'll definitely get back to. We are past the session end time, so I would like to take this opportunity to thank you again, and we will definitely get back to you with any unanswered questions. Thank you everybody for attending the session.